Let's talk about concavity. The graph of a differentiable function, y equals f of x, is concave up on an interval I if f prime of x is increasing on I, and concave down on an interval I if f prime of x is decreasing on I. Well, these definitions are nice. So this tells me that if I have tangent lines over an interval that are getting steeper, increasing, then I have a shape called concave up. This is telling me that if I had tangent lines whose value was decreasing, slope's value was decreasing, I'd have this shape called concave down. I thought we'd take a look at two examples to see what these really mean. In my first example, I'm looking at the graph of y equals x cubed, this very typical cubic function. I've taken a first derivative because I want to talk about the slopes, right? We're supposed to have a concave downward shape when the slope is decreasing and a concave upward shape when the slope is increasing. I've written a number line test for the first derivative just to justify the fact there is no relative extreme values. This function is always increasing, always going up from left to right. I know there's a horizontal tangent line at the origin because the derivative is 0 there. But now I just want to think about these tangent lines. The slope of each tangent line is computed by plugging in x and getting out this y prime, 3 times the x chosen squared. What I know is that with the exception of the origin, my slope is always positive. And so down here, I see a very steep tangent line. And then as I get closer to the origin, the slope is going down. This must be that concave down shape. On the other side of the origin, I plug in larger and larger x's and my slope gets steeper. So this is my concave up shape. And to exaggerate them, on the left-hand side, I kind of see this shape that looks like if it was rained on, water would run off. And on the other side, I see this shape where if it was rained upon, rain would catch in it like a bowl. So this shape is concave up, and this shape is concave down, just depending on how my tangent line's slopes are behaving. The slope is decreasing, and I get this concave down shape, and the slope is increasing, and I get this concave up shape. Let's look at one more example. Here I have the graph of e to the minus x squared, probably not drawn too well to scale because I did it by hand, but it makes a nice example. You may never have graphed this function before, so it might be a good idea to pause the video and maybe grab your graphing calculator and see if you can graph it over a similar window that I have here. Okay, so assuming that you've looked at that graph, well, I could do a first derivative test for local extreme values. I can see that there is a critical point at 0, and I'm increasing and then decreasing. Well, e to the minus x squared is always a positive number, so just depending on the sign of x to figure out what's going on here. Negative times a negative is a positive, so over here I have that going up. A negative times a positive over here, and my graph's going down. But if I focus in a couple places, here my tangent lines are going up, right? The first derivative is increasing, so over here is that concave up shape. In the middle, my tangent lines decrease. I get here, and they keep going down. In fact, on the other side, they're negative. So here I have a slope that's steep, less steep, a horizontal tangent line, a slope that's negative, and more negative. And that's that concave down shape. And then finally here, my slopes are negative, but getting closer to 0. So that's increasing, because if this tangent line slope was something like, and I'm making this up, but -2, then this one is like -1. Well, -2 is a lower value than -1, so that's increasing, and that's that concave up shape. I don't know if I said I was going to do 2 or 3 examples, but here at the end of the video, I feel like doing at least one more pair of examples. Let's just look at the graphs of y equals x squared and y equals 1 minus x squared. Y equals x squared, just our parabola. Y equals 1 minus x squared is that parabola flipped upside down and shifted up 1 unit. I probably should have drawn a scale here and made my graph a little better, but we're very familiar with these graphs, and I think that's probably good enough. Well, let's just imagine the tangent lines in each picture. See if you can find where these are concave up and concave down. Pause the video and give yourself a shot at it. Okay, well, that's a very steep negative slope, and the slopes get less steep as I get closer to origin. And then they increase. Technically, the slope is always increasing. This is that concave up shape. The whole graph is concave up because as I move from left to right, the first derivative is always increasing. It's very negative, it's zero, and then it's very positive. Over here, that upside down parabola, my slopes are decreasing always, even on this side where the slope gets more and more negative as x goes from left to right. In our next video, we'll pick up a test for concavity.